Okay, so now we go to the second part of your trigonometric integrals, which is your transformation by trigonometric functions. So if you look at your slide, so most likely we're going to have three pairs that we need to discuss, and then we'll go through each type, and each type will have two cases for that we need to discuss or need to go through. So again, in these types of process for the three types, we're going to utilize the Pythagorean identities. So Pythagorean identities. And as observed in the different types, so sorry, wrong spelling. So as you can see, we have the sine and cosine pair up, tangent and secant, and then cotangent and cosecant pair up. So if you try to list down the different Pythagorean equations, so type A pertains to sine squared theta plus cosine squared theta is equal to 1. So as you can see, sine and cosine pair up. So next is your tangent and secant. So we have 1 plus that's tangent squared theta plus 1 is equal to secant squared theta. So tangent and then secant. And lastly is you have your cotangent and cosecant. So that's 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, so that's cotangent and cosecant. So for example, we have to derive your Pythagorean equations. So what you need to do is you just have to create a right triangle. So you might wonder how did those formulas got their equations. So coming from a right triangle. So again, according to Pythagorean theorem, so let's say these are your sides. So again, according to Pythagorean theorem, so the square of the sides is equivalent to the hypotenuse, the square of the hypotenuse. So to determine these three Pythagorean identities, so we need to let one angle be equal to theta. So let's say this particular angle. And then next is we divide everything first by c squared to get the first formula. So what happens is we have a squared all over c squared plus b squared all over c squared is equal to 1. So simplifying further is we have a all over c squared, b all over c squared is equal to 1. So notice that in your drawing or in your diagram, so a over c pertaining to the angle is that's opposite side all over the hypotenuse. And with respect to the theta angle, so that trigonometric function is your sine function. So we have sine squared theta. So diba, if again we are going to determine the trig function, so excuse me. Okay, so sorry for that one. So I need to go to the Kwanzaa. Okay, so going back, so again, if we try to determine your trig function pertaining to the angle, so we have sine. So sine theta is equal to opposite side over adjacent, opposite side over the hypotenuse, so that's A all over C. So notice that A over C is equal to the sine theta. So that's why we can replace this term with sine squared theta. So again, squared because of the squared term or the squared exponent outside. So next is B over C. So B over C, that's adjacent side all over the hypotenuse. So cosine theta is equal to B all over C. So again, B over C is equal to cosine theta. So we can replace this one with cosine squared theta is equal to 1. So that's for the first formula. So for the other formula is you just have to divide. So earlier we divide by c squared. so to so to determine the rest of the formula is we divide by b squared next. So next is we have a all over b squared plus 1 c all over b squared. So again, looking at your triangle a over b, so that's opposite all over adjacent side. So that will be tangent theta. So again, pertaining to the angle theta. So opposite side is A, adjacent side is B. So that's A all over B. So again, A over B is equal to tangent theta. So for C over B, so that's hypotenuse all over the adjacent side. So that's second function, di ba? So second function is B all over C all over B. So that's second. So sorry. So let me erase it first. So that's C all over B. So C over B is equal to secant theta. So simplifying is we have tangent squared theta plus 1 is equal to secant squared theta. So lastly is we divide by a squared. So we have 1 plus b all over a squared is equal to c all over a squared. So b over a is cotangent according to the diagram. So let's make it shortcut because we don't have any more space. And then c over a is hypotenuse all over adjacent, hypotenuse all over opposite side. So that's cosecant squared theta. So this is how you derive your different Pythagorean identities. So if you forgot the format, so instead of cheating or instead of going through your Codigo, so you might as well derive your equations. So this is useful especially when you go to board exam. So sa board exam, one ay Codigo ba sa board exam. So you have to really memorize the equations. Okay. So by the end of this session, so we need to finish by type B. So that by next meeting is we can have your type C and then we can have a 1 meeting break so that you can do your problem set for your asynchronous activity. So let's start with type A. So again, for each type, we're going to discuss 2 different cases. And of course, we discuss also examples along the way. Okay, so for type A, so that's the integral of sine u to the power of m cosine u to the power of n du. So take note that m is the exponent of your sine function, and then n is the exponent of your cosine function. So in case number 1, so either m or n is odd and positive integer. So meaning either m or n is odd or positive. So we have to observe, or we have to determine whether your m or n exponent is odd and positive. So let's say your m, the exponent of your sine function, is odd. So we need to factor out sine u du. Okay. Then upon factoring sine u du, then we apply. So the term here is then we then apply, or you can just say we replace or we substitute sine squared u is equal to 1 minus cosine squared u. So you could replace this one with replace or substitute with this particular term. Now if n is odd, the exponent of the cosine function, so that's the reverse of the statement earlier. So instead of sine u du, so we factor out cosine u du, and then apply or replace or substitute with cosine squared u is equal to 1 minus sine squared u. Okay, and then after this step is you use your basic process of integration. So for you to be able to appreciate the case number 1, so we go to some examples. Okay, so again, we try to write your different guide in the upper right. So again, m or n should be odd and positive. Okay, so again, if m is odd, so we need to factor out your so if m is odd, so we need to factor out sine u du. If n is odd, so we need to factor out cosine u du. So next is, so if m or n is odd, so we need to apply or replace or substitute the corresponding Pythagorean equation. So so sine squared u is equal to 1 minus cosine squared u. So for the other one, if your exponent is pertaining to the odd function, the n function, so we have cosine squared u is equal to 1 minus sine squared u. Okay, so after these steps, so what we normally do is we use the u sub technique, and then we integrate. Okay, so we have 1, 2, 3, and 4 steps. Okay, so starting off with your exponents. So again, we need to observe your exponents first. So this is the m exponent, the exponent of the sine function. The next is the negative 5. So that's the exponent of the cosine function. That's n. So since the other one is negative exponent, so it doesn't apply anymore to case number 1. But in the sine function, so it applies to case number 1 since it's odd and it's positive. So meaning we have the m series. Okay, so m, then this one. Okay. Okay, so first step is, since we determined that m is odd, so next step is to factor out sine u du. So sine squared, so we take one sine outside the equation, then cosine negative 5x multiplied by sine x dx. So notice that I factored the term on the right side together with dx, because again, factor out sine u du, sine u du. So most likely your dx is on the right side, so we need to make it side by side with the dx, your sine function. So this is our sine x dx. So most likely the purpose of which also, that's why it's on the right side, because this will be our derivative of your u sub later. This will be a candidate for your derivative. Okay, so that's why it's paired up with dx, because this is most likely a candidate for your du function or your derivative in the u sub. Okay, the du in the u sub. So that's why it's placed on the right side for us to easily observe that this particular term is the du later on. Okay, so next step is we replace by 1 minus cosine squared. So replace sine squared u with 1 minus cosine squared u. So replacing, so we have 1 minus cosine squared x times cosine to the negative 5x, then again sine x dx. Okay, so next is we distribute. So we distribute this one. So what you factored out is don't distribute again, because of course you'll repeat the process of factoring out your sine x. So yeah, so just place your factored out term on the right side and don't deal with this one until the u sub process later on. Okay, so you have that's cosine to the negative 5x. So cosine squared, then cosine negative 5, so that's cosine negative 3 of x, then sine x dx. Okay, so this time is we can now use the u sub technique since we are done simplifying your integrand. So again, as what we have mentioned earlier, your sine x dx, the factored out term earlier, is a candidate for your derivative of your u sub. So since this one is sine x dx, so most likely our u is your cosine, because the derivative of cosine is negative sine. So cosine x, then derivative of your cosine is negative sine dx. So that's why I termed it as a candidate for du, because not all the time that your value of your sine x dx is always du. So in this case, your final value for your du is negative du for your sine x dx. So that's why I said that it's a candidate, because it might be du over 2, negative du, or any value of the du later that we have determined in the u sub process. So sine x dx. So this one is our negative du, and of course this one is our u parameter. Okay, so simplifying even further, so we have u to the negative 5 minus u to the negative 3, and then negative du. Okay, so next is we can now distribute, or you can now so let's take the negative sign outside the equation first. So that's negative u to the negative 5 u to the negative 3 du. So you can now integrate. So that's negative. So that's u to the power of negative 4. So n plus 1 all over negative 4. So minus pa jud. So minus sign. Then negative, the negative here. U to the negative 2 all over negative 2. So n plus 1, negative 3 plus 1 is negative 2 all over negative 2 plus c. So simplifying even further is you have u to the power 4 all over 4. So 3 negative sign minus the negative 1, the negative number in the denominator. So that's minus. So this one is negative 4 there. So you have u to the negative 2 all over 2 plus c. So replace your u parameter again. So we have cosine to the negative 4 x all over 4 minus cosine to the negative 2x all over 2 plus c. Okay, so if you don't want any negative exponent, so you can also express your answer in this manner. So that's 1 all over 4 cosine x minus 1 all over 2 cosine x plus c. So this is the correct answer also. Or if you don't want any fraction, so 1 over cosine, so to the negative 4 din eh, negative 4, positive 4. And this one is squared. So if you don't want any fraction, so 1 over cosine is second. So you have second to the power of 4 x all over 4 minus second squared x all over 2 plus c. So this can be the correct answer also, depending on how you simplified your final answer. Okay, so any more questions? So any questions regarding the first example? Okay, so I think, okay, so there's none. So as long as you go through the guide of the different cases, so I think you can answer the problems. Okay, so let's go to the second example. So again, if you try to observe our exponents, so the m exponent is even, so we cannot utilize this one. But the cosine exponent is odd and positive. That's the n parameter. So meaning n is odd and positive. Okay, so again, next step is to factor out cosine u du. And the next is we replace cosine squared u with 1 minus sine squared u. Okay, and then use U sub technique. So again, 1, 2, 3, and 4 steps. Okay, so since we're done with the first part, you've determined that your n exponent is odd. So next step is we factor out cosine u du. So integral of sine to the power of 4 2x, and then cosine, so instead to the power of 5, so that's 4 2x. So again, what you factored out is you place on the right side together with dx. So cosine 2x and dx. Okay, so this one is already correct. So in the third step is we replace your cosine squared u with 1 minus sine squared u. So looking at your cosine function, so that's to the power of 4. Ba to the power of 4. So we need to do this twice. Or you can replace this one with 1 minus sine squared u, but squared siya. So it will be squared to get the same value of the degree of fourth power. Okay, so replacing. So we have sine to the power of 4, 2x, then 1 minus sine squared 2x squared. Okay, so again, that's why it's squared, because we have a fourth degree here. So if you try to break this one into its corresponding parts, so that would be cosine squared 2x, cosine squared 2x. So you have two values or two terms for 1 minus sine squared u. So that's why I just simplified it immediately. That's 1 minus sine squared 2x squared. Okay? Then cosine 2x dx. So bracket. Okay? So next is we need to expand this squared term. So you have sine to the fourth 2x. So again, this one is difference, the square of difference. I mean, how do you call that one in algebra? Basta ka ng a given binomial, then yung square. Difference of two binomials. So I think that's a term. So you have 1 minus 2 sine squared 2x, then plus sine to the fourth 2x. Okay, then cosine 2x dx. Okay, so next is we distribute. So distribute to each of the term inside the parenthesis. So what happens to the equation is now you have sine to the fourth 2x minus 2 sine squared, that's to the 6, two x, and then plus sine to the eighth 2x, then cosine 2x dx. So before we integrate, so let's try to arrange the integrand in descending order of degree. So what comes first is your eighth power. So sine 8 to x minus 2 sine to the 6 of 2x, then plus sine to the fourth of 2x, then cosine 2x dx. Okay, so I think now we can use the u-sub technique. So in the third step, we are now done. So in the fourth step is you now use your u-sub technique. Okay, so again, your cosine 2x is the candidate for your du parameter. So to get the derivative of cosine 2x, so obviously the u parameter of which should be sine for us to determine cosine 2x as its derivative. So notice that what we have declared as your u function, the sine function, is present in the integrand also. Okay, so du, so derivative of sine is cosine 2x, then derivative of the angle is 2 dx. So what you have here is you have 2 cosine 2x dx. So divide by 2, so your du is du over 2. Then cosine 2x dx. So this one is your du all over 2. And this will be your u parameter, each term. So 3 terms to be exact. Okay, so replacing with u sub, so u to the power of 8 minus 2 u to the power of 6 plus u to the power of 4, then du all over 2. So simplifying even further, so let's try to squeeze this one inside this small space. So factoring out 1/2, so this 1/2, so integral of u to the 8 minus 2u to the 6 plus u to the 4th du. Okay, so now as we can now integrate, so you have 1/2. So again, distribute 1/2 with each respective derivative, integration process that you're going to have. So that's u to the power of 9 all over 9 minus 1/2 times 2 times u to the 7 all over 7, then plus 1/2 times u to the 5th all over 5 plus c. So multiplying, so you have u to the power of 9 all over 18. So negative 1/2 times 2, so that will only be u to the power of 7 all over 7. Then lastly is you have u to the power of 5 all over 10 plus c. So final answer is, so replace u with sine 2x. So that's sine to the 9th of 2x all over 18 minus sine to the 7th of 2x all over 7 plus sine to the 5th of 2x all over 10 plus c. So this is your final answer. Okay, so questions for the second example. Okay, so just try to solve this one again on your own with the guide of the recording later, so that you can have your own style of generating your solutions. Okay, so let's proceed with the second case. So in the second case, so both m or n are even and positive integers. So this should be end. So both m or n. So it could be m or n are even and positive integers, or if m is if the sine function is present in the equation and there's no cosine function, so it could only be m. It could also be n. So depending on, so for example, in example number 2, so it's only the sine function. So just ignore this one because this one is not included in the slide. So I forgot to edit this one. Okay, so if m and n are even and positive integer, so we need to use these formulas. So I'm not sure if this one is called the reduction formula or the reduction identity. So just try to search this one online. But in my case, so if you look at the equation, so that's just coming from the half angle identity we discussed in the previous meeting. So again, coming from the half angle identity. So for example, we have sine theta all over 2 is equal to plus minus square root of 1 minus cosine theta all over 2. So getting the square of both sides is we have sine squared theta over 2 is equal to 1 minus cosine theta all over 2. So as you can see, this one are similar equations, but they have different terms of declaring their angle. So for example, this one here is u, the other one is theta over 2. And on the right side, you have 2u, but here on the right side, you only have theta. So it depends on the reference that on how they declare their different terms. Okay. So for cosine, it's still the same. So coming from the cosine half angle, so plus minus 1 plus cosine theta all over 2. So getting the square of both sides, so that's cosine squared theta over 2. Then 1 plus cosine theta all over 2. So notice this one. Again, they are similar, but they have different declarations of their angles. So again, it all depends on the reference. So it could be that this author he wants to represent their angles this way, and then the other author is in this manner. So as long as you know how to apply the different variables being presented in the reference, so it's okay to use different references. So I'm going to show you later what's the difference of using this u parameter as the angle and the half angle I'm using with theta over 2. Okay, so let's try to solve the first problem for us to appreciate case number 2. So we have the integral of sine squared 2x cosine squared 2x dx. So again, we try to examine the exponents. So again, both m or n should be even and positive. So as you can see here, both are even and positive. Okay, so both applies. So meaning in our equations, so we need to replace sine squared u with 1 minus cosine 2u all over 2, and then replace cosine squared u with 1 plus cosine 2u over 2. Okay, so I think in this case we only have 2 steps because once you replace this one with its corresponding identity, so what's left for you to do is to integrate the cosine function since it already simplified. Okay, so before we replace with 1 minus cosine 2u over 2, so again we need to declare first the angle. So again, the angle u. Okay, so here our u is 2x, 2x. So u is equal to 2x. So for us to get 2u, so we need to multiply everything by 2, and then you have 2 times u is equal to 4x. So again, what's the difference with the theta parameter that I have mentioned earlier? So again, in the theta parameter, so you have sine squared u, oops, so sine squared theta over 2 is equal to 1 minus cosine theta over 2. Then the other one is cosine squared theta over 2 is equal to 1 plus cosine theta over 2. Okay, so here our theta over 2 here. So theta over 2 is 2x. 2x. Then getting theta, so just multiply 2 to the other side. So theta is 4x. So as you can see, there's no difference. So it's exactly the same as what we have declared earlier. So as long as you know how to determine your angles for such equations being presented by the reference, so whichever type of equation you're going to use, so the resulting answer will still be the same. Okay, so now we replace with 1 minus cosine 2u first over 2. So 1 minus cosine 2u or theta. So that's 4x. Then the other one is 1 plus cosine 4x all over 2. So sum on, so the square, so the square of, so the difference of two squares, diba? In the numerator. So what you'll have here is, so again, if we take this one step by step, 1 minus cosine 4x, times 1 plus cosine 4x all over 4 dx. So simplifying, taking 1/4 outside the integral symbol, and then this one is we multiply or expand the numerator. So this one is the difference of two squares. So 1 minus cosine squared 4x dx. So take note that in the second term, it's still squared, di ba? And also take note, or if you notice something, 1 minus cosine squared 4x can be replaced with this corresponding Pythagorean equation, which is the sine squared theta. So again, if you try to write this one on the right side, so sine squared theta plus cosine squared theta is equal to 1. So we have sine squared theta is equal to 1 minus cosine squared theta. So we can simplify it even further. So this becomes 1/4 the integral of sine squared 4x dx. So since this one is squared, so of course we try to use the technique again. So again, since this one is squared, so we go back here. So u is equal to 4x. 2u is 8x. Okay. So we now have 1/4. Then we have 1 minus cosine 8x all over 2 dx. So expanding. So you have 1/2. Or if you don't want the 1/2, so you can get the 1/2 outside the equation. So 1/4 times 1/2, then the integral of 1 minus cosine 8 of x dx. So you have 1/8 integral of 1 minus cosine 8x dx. So integrating is, the first term is just x all over 8. Second term is 1/8. Then again, the integral of cosine is sine. So again, recall that if you have a coefficient of the angle, that's 1 over a. So that's 1/8. And then sine 8x plus c. So the final answer is x all over 8 minus sine 8x all over 64 plus c. So this one is your final answer. So notice that we used case number 2 twice because we encountered even integers or even exponents twice in the process. Okay, so questions for the first example? Okay, so I think there's no question. So let's try to go to the second example. So next is the integral of sine to the fourth 2x. So again, we observe that our sine function is even. So m is only present, there's no n. So even if there's no n, so again it's okay because again the difference in the equations for the sine squared function and the cosine squared function is just the operation. So for sine is we have 1 minus cosine 2u all over 2. Then for the cosine, it's just the opposite operation of this one. So we have 1 plus cosine 2u all over 2. So again, it won't matter if the other function is not present in the equation. Okay, so next, so this time let's try using the theta instead of the u parameter. So sine squared theta over 2 is equal to 1 minus cosine theta all over 2. Okay, so the first step is done. Then we now replace with this particular identity. So again, before we replace it or we make the substitution technique, so we try to declare first your angle. So we have u is equal to not u there. So sorry if may apelido nga u dire. So theta all over 2 is equal to 2x. Okay, 2x theta over 2. So multiply 2 to the other side. So theta is equal to 4x. Okay. So take note also that since this one is only squared, and then this one is to the power of 4, so we need to square it upon replacing or upon substituting your 1 minus cosine theta over 2 parameter. So for you to be able to be guided, so this one is 1 minus cosine 4x all over 2. So again, squared. Okay, dx. Okay, so we now have 1 minus cosine 4x squared all over 4 dx. So getting the constant outside, so you have 1 minus cosine 4x squared dx. So next is we expand. So we have 1/4, then expanding the binomial. So we have 1 minus 2 cosine 4x plus cosine squared 4x dx. So if we try to rearrange according to the degree, descending order, so the first term should be the squared function of cosine. Then next is the linear degree of the cosine. Then lastly is your constant. So take note that we have a cosine function in the first term, cosine squared function. So again, we go back here in the upper right. So we can now say that we are going to have two different process of the second case. So n is even again. Then we need to replace with cosine squared theta over 2 is equal to 1 plus cosine theta all over 2. Okay? So again, before we make the replacement or the substitution process, so we need to declare first your angle. So theta over 2 is equal to 4x. So theta is 8x. Okay. So replacing or substituting your 1 plus cosine theta over 2. So you have 1/4. The integral of, so the first term is 1 plus cosine 8x all over 2 minus 2 cosine 4x plus 1 dx. Okay, so expanding, so you have 1/4, then separating the two terms here because we can create two terms here. So that's 1/2 plus cosine 8x all over 2 minus 2 cosine 4x plus 1 dx. So we can combine 1/2 and the one constant. So 1/4, so I'll make it step by step for you to be able to see the flow of the process of calculation. So cosine 8x over 2 minus 2 cosine 4x. So 1 plus 1/2, that's 3/2 dx. Okay. So integrating, so we now have, so let me place it one here lang, okay, because I think it's a very long equation. So 1/4. So again, don't forget to multiply the constant term to each integration process. Okay. So 1/4. Then again, we have a 1/2 here. So integral of cosine 8x. So that's 1/8 because we have a coefficient of the angle, that's 8. Then sine 8 of x. Okay. Minus 1/4 times 2 times again integral of cosine 4x. That's 1/4 sine 4x. Then lastly is your constant term, that's 3/2. Oops, let's make it in order. So lastly is you have 1/4 times 3/2 times x plus c. So the integral of a constant is x. Okay, so simplifying is that the first term is 1/4 times 1/2 times 1/8, that's 1 over 64. So the first term is sine 8x all over 64. Okay, so 1/4 times 2 times 1/4, so that's 1 over 8. So that's sine 4x all over 8. So minus the minus. Then lastly is you have plus 3x all over 8 plus c. So this is your final answer. So I think we cannot simplify even further. So that's your final answer. Sige. So 3/2 is, so let me change the color first. So 3/2 is this one, 1 plus 1/2. So that's why it's 3/2. Okay. Okay, you're welcome. So Any more questions or clarifications? Okay, so if you don't have any questions, so let's proceed with type B. So type B is we now go to the tangent and secant pair up. So again, if you forgot the particular Pythagorean identity that pertains to tangent and secant, so try to derive it or try to write it down here. So tangent squared theta plus 1 is equal to secant squared theta. So again, it depends on the reference or the author. So you can manipulate the equation and present it this way. So for case number 1, type B in the secant and tangent tandem. So if n, the exponent of your secant function, is even and positive integer. So that's why it should be an integer, because if we are dealing with a fraction integer, so that will refer to radicals already. So radicals are katong mga square roots. So that's why we're only referring it to integers, because integers are whole numbers. So 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, negative 2, negative 3, and so on and so forth. Okay? So factor out secant u du. So again, the factored out term will be the candidate for the derivative of u, the du. Okay? Because again, in your derivatives, the derivative of your tangent is secant squared u du. Diba? So that's why we need to factor this one out and then have its purpose later in the u sub technique process. So after factoring out sec u du, so we need to apply this particular Pythagorean identity. Okay. So for you to be able to appreciate case number 1, so let's try to solve the first example. So again, it states that n, the exponent of the secant function, should be even and positive. So next step is for us to factor out secant squared u du. And then next is to apply if there is still left in the one. So for example, you factored out secant squared from secant squared to the power 4. So if there's still a secant squared left, so what we need to do next is we replace your secant squared u with 1 plus tangents. Okay, so first step, second step, third step, then the fourth step is your u sub technique, if ever. Okay, so n is even and positive, so we are done with this one. So next step is factor out secant u du. So next is we factor this one out. So notice that in the equation, it's already factored out. Or if we factor out this one even more, so that will result to so let's say we factor it. So we factor this one secant squared u. So that will be 1 times secant squared u du, di ba? All over the square root of tangent u. Okay? So next is we replace with secant squared u with 1 plus tangent squared u. So notice that in 1, there's no extra secant squared term left. So again, what I mean by this is, for example, we have secant to the power of 4 u. So if you try to factor out secant squared in the second step, so what will happen is you have secant to the power secant squared u, and then secant squared u du. Diba? So this will happen if our exponent is to the power of 4. Now this one again is the factored term in the second step, so we don't have to deal with this one up until the u sub technique. Now in the third step, this only applies if there is a secant squared term left in the equation. So for example, this one. So this one will become 1 plus tangent squared u, and then the factor term secant squared u du. So that's the case for secant to the power of 4. But in this case, since we only have one constant left in the numerator, and there's no other way to replace with the third step, so we can skip this process and we go immediately to the fourth step, the u sub technique. So getting the u sub, so more likely the integration process is a bit tricky because you need to make adjustments along the process of integration. As long as you understood the process, so you can get the final answer. So let me erase this one again. So since the given parameter is u already, so we can use another variable. So let's say z. So again, since this one is our du, so automatically our z should be tangent u because its derivative is secant squared u du. Okay, so getting the final equation is we have the integral of dz all over the square root of z. So expressing this one in exponential form, so z to the power of negative 1/2 dz. Okay, and the next is we integrate. So that's z, so negative 1/2 plus 1, that's 1/2 all over 1/2 plus c. So that's 2z to the power of 1/2 plus c. So you have tangent, 2 tangent to the power, so that will be 2 tangent of u to the 1/2 plus c. So this one is the possible answer, or you can also express this one in its radical symbol. So that's 2 square root of tangent u plus c. So this one is also a possible answer. Okay, so I think it's awkward for you to write tangent in this manner. Tangent 1/2 u, di ba, murag it's not appropriate for the fraction exponent to be expressed that way. So if it's a whole number, so I think it's okay because you can have tangent squared u. But if it's a fraction, so I think it's much better if you enclose your trigonometric function with a parenthesis, then declare the fraction exponent. Okay, so questions for this example. So you might be confused on the steps, but again, um, you need to be careful with the steps. So, for example, ganina, since we don't have any second squared left, so we can skip this one and go straight immediately for U sub technique. So you can adjust with the steps. So not totally go away with the process, but just skipping some steps because they don't apply anymore in the process of the integration. Okay, so questions for this example. Okay, so if you don't have any questions, so you can we can now proceed with the next case. So in the second case, so m is positive, so that's the exponent of the tangent function. So the tangent function should have a odd and positive integer. So next is so after determining that your tangent function is an odd and positive integer, so we need to factor out sec u tan u. So again, the factored term will be the candidate for the derivative of u in the u sub technique. Okay, so if there's a tangent squared left in the equation, so we need to replace your tangent squared with secant squared u minus 1. So again, notice that your derivative of u is sec u tan u, because again in our derivatives, the derivative of secant, so the derivative of secant u is sec u tan u du. So most likely this will be our u parameter in the example later, and this one is our probable du parameter, because again du can shift with the simplification process, so it could be negative du, du over 2, 2 du depending on the u sub process. Okay, so let's try to have the last example before we dismiss. Okay, so we have sorry. Okay, so again we need to determine that the exponent of the tangent function should be odd and positive. So m is odd and positive. So since this one is true already, so we go on to the next step. So that's factoring out secant u tangent u du. Okay, then if there's a tangent squared left, so we need to replace it with secant squared u minus 1. Okay, and then go to the u sub technique. So that's 1, 2, 3, and 4. Okay, so if we try to factor out sec u tan u, so notice that we need we need to factor out secant u also. So for us to visualize even properly with the factoring process, so we move the second x function in the numerator. So we have tangent of 3x, and then in exponential form, your second term will be second x to the power of negative 1/3 dx. Okay? So again, we need to factor sec u tan u du. So getting one tangent, that will be tangent squared x second x. So getting 1 second from negative 1/3, so that will be negative 4/3. Then we have sec u, so sec x tangent x dx. Okay, so why it's for negative 4/3? So again, if negative 1/3, so if we take 1 away from negative 1/3, so that will be, so again, shortcut, minus 3/3. So that's negative 4/3. So again, if we multiply this one again, so 4/3 plus 1 is negative 1/3. And then tangent squared times tangent, that's tangent cube. Okay? So it still equates to the previous line. So what I give sub, so there's no change, but only in the format, or only in the equation, because I mean the equation is still balanced because we only factored a particular term. Okay, so we are done with this step. So next is we replace tangent squared u with secant squared u minus 1. So notice that we still have a tangent squared left. Unlike the previous example, so since there's no secant squared left in the process, so that's why we skipped the step and then we went immediately for the u sub technique. So this one becomes secant squared u minus 1, and then secant x din siya, x negative 4/3 secant x tangent x dx. So distribute to each of the term. So the first term is secant, so for the first term, 2 minus 4/3, so that will be 2/3, diba? Sakto? So secant x 2/3 minus secant x negative 4/3. And then sec x tangent x dx. Okay? So again, why this one is 2/3? Because 2 minus 4/3, so again using the shortcut, that will be 6/3, because 6/3 is equal to 2 minus 4/3. That's 2/3. Okay? So next step is we use the u sub technique. So again, this one is our candidate for the du parameter. So again, if we know that this one is the derivative, so our u should be secant x, because its corresponding derivative is sec x tangent x dx. Okay, so u parameter, du parameter. So what we'll have now is the integral of u to the 2/3, then minus u to the negative 4/3 du. So integrating is we have 2/3 plus 1, that will be 5/3 all over 5/3 minus u, so negative 4/3 plus 1, that will be negative 1/3 all over negative 1/3 plus c. Okay, so simplifying is we have 3 u to the 5/3 all over 5. So minus, then minus, so it will be plus u to the negative 1/3, 3 u to the negative 1/3 plus c. So replacing with the second function, so second x to the power of 5/3 all over 5 plus 3 second x to the power of negative 1/3 plus c. So this is your final answer. So questions for this example. Okay, so if there's none, so you can start answering partially your next problem set, which is the deadline of which will be next Friday.